Okay, moving on with rate laws for video 2.1.2, we're going to talk a little bit more about the rate law. And one thing that we need to just clear up right away, one thing we just need to put out there is that products don't really matter in rate laws. So we don't take into account the products. Those are never going to go in the rate law. So maybe just write yourself a note. Products are never included in rate laws. Alright, so never have to take into account your products. Okay, so let's look at this first sentence. The rate law describes the relationship between a reaction's rate and the concentration of the reactants, as we saw previously. In general, as the concentration of the reactants increases, so if we get more reactants, the rate is also going to increase. So the rate increases. And the question then is why? Well, if we think about it, if we have the concentration increasing, we're going to have a whole lot more particles in a smaller area, or in the same area rather. And those particles are going to be more likely to bump into one another. And we know that based from the kinetic molecular theory, particles have to collide in order to react, right? So the number of effective collisions then that result in a reaction will increase, so the rate will increase. So the number of effective collisions that result in a reaction increases. That just makes sense. You have more particles are more likely to run into each other. Okay, let's look at an example here. Consider the hypothetical reaction of A plus B plus C goes to products. So again, we really only care about A, B, and C. We don't really care about products. Data from the 4 experiments is shown on the table to the right. The rate law for the reaction was found to be rate equals K, and K is the rate constant, times the concentration of A squared, so this is second order with respect to A, times the concentration of B to the first power, so this is the first order with respect to B, and the concentration of C to the first power, so this is first order also with respect to C. Find the rate of the reaction for trials 2, 3, and 4 without using direct math. So basically we're going to use some comparisons here to try to figure out what these rate laws are. Okay, so we're looking at trial 2 first. So trial 2, we're going to compare trial 2 to what came right before it, to trial 1. And we can see here that when we compare the concentrations of A, B, and C, some change and some don't. So A increases, right? The concentration of A is going to be changed here. B was left the same in both trials, and in both experiments here, C was also left the same. So the only thing that was varied was the initial concentration of A. And in this case, we can see that that was tripled. So 0.5 tripled is 1.5. And it's asking us to find the rate here. Okay, so from trials 1 to 2, and write kind of small because there's a lot to write in this little area. So from trials 1 to 2, the concentration of A triples, while the concentration of B and the concentration of C remain the same. Since the reaction up here is second order with respect to A, so that means there's a little 2 in our rate law, and you wouldn't know that without being given the rate law. You can't tell that from the chemical reaction. You have to be given this rate law to be able to tell that. So since we know that the reaction is second order with respect to A, so since the reaction is second order with respect to A, the rate is going to change by 3 to the second power. So where do these numbers come from? We said that the concentration of A triples, so 3, And we said that the reaction is second order with respect to A. So the concentration triples here, so we're going to sub in a 3 for A squared because it's second order. So it triples second order. So the rate changes by 3 to the second power, or 3 to the second power is 9. So we can say that the rate equals 9 times whatever our concentration, or whatever our original rate is here. So 9 times whatever this rate is, that's what this rate should be here. So 9 times 0.0100 moles per second, which equals 0.090 moles per second. Okay, so that should be our rate for trial 2, 0.090 molar per second. Okay, let's look at trial 3. I'm just going to change color here as there's a lot of writing in a small space, so we can keep these separated. Okay, so trial 3, let's look at trial 3. We can see A doesn't change. B changes here, and C doesn't change. So this one we're going to use to figure out our B. So B actually increases 9-fold, so 9 times. So 0.3 times 9 is 2.7. So we can see this is a 9-fold increase. So we can say that the concentration of B increases 9-fold. While the concentration of A and the concentration of C remain unchanged. And that's from trials 2 to 3. So since the reaction is first order with respect to B, and B is the one that's increasing 9-fold here, I want you to pause the video and see what you think this number is going to be here. So what's the rate going to be? Remember, it increases 9-fold, and it's first order with respect to B. Okay, so since the reaction is first order with respect to B, the rate changes by, let's see if you got this, 9 to the first power. So it's a 9-fold increase there, and it's first order. We can tell from our rate law up here there's a 1 with respect to B. So, or that's just 9. So the rate is going to be equal to 9 times whatever it was on trial 2, because remember, we're comparing trials 2 and 3, so we're going to multiply it times this trial 2, what it was before. So rate equals 9 times 0.09 molar per second, and that should be 0.810 molar per second. So I'm going to go ahead and write that up here. 0.810 molar per second. Okay, so last one, trial 4, switching colors again to keep these separate. Trial 4. We're going to look at trial 4, and we are going to compare that to trial 2 because we have the least change there. So trial 2, see, A changes, B doesn't change. We want as many constants as possible. And C here also changes. So we have 2 concentrations or 2 reactants changing. So we can say that A, the concentration of A, and the concentration of C, let's see, what do they do? So A, we're comparing reactions 2 and 4, so that doubles. B stays the same. C also doubles, so they both double. While B, the concentration of B, remains unchanged. From trials 2 to 4. Since the reaction is second order with respect to A, so we saw up here second order with respect to A, is going to be first order with respect to C, and first order with respect to C, the rate changes by 2 to the second power times 2 to the first power. So we have that A squared, that doubles, and we have 2 to the first power, so that's first order. So we're going to multiply these together. And when we do that, that should be or 8. So the rate then is going to be equal to 8 times 0.09 molar per second, or 0.720 molar per second. So 0.720 molar per second. Okay, so now that we've found our rates above here, we're going to do something similar. We're going to go from the rates now. We're going to try to find this rate law. So for this reaction below, for our next example, we want rate equals K times whatever it is to the X, Y, Z. So we're trying to figure out what this 2, 1, and 1 are, what this X, Y, and Z are for this next reaction. Okay, so example, consider the reaction and the kinetics data collected. Here's our reaction. And we're going to find the rate law for the reaction. So there are 4 trials done for this reaction, varying the initial concentrations, and the rates are actually already given to us. So we're just basically going to compare reactions. So remembering what we did above here, we tried to compare reactions where, for example, when we're trying to find B, A and C were the same concentrations, and B was the only variable that was changed. That's what we're going to try to do here. So first I'm going to try to find the rate with respect to MnO4 minus here. So for MnO4 minus, I'm going to compare 2 trials. So which 2 trials would you compare for MnO4? Go ahead and pause it and try to find the 2 trials that you would compare. Okay, so hopefully you have chosen trials 1 and 2 because the MnO4 is different, and so we can find what the rate law is with respect to MnO4 here, but our ClO3 and our H+ haven't changed, so we can just not bother with those at all. So compare trials 1 and 2. And when we compare the trials, really we just divide one by the other. So I'm going to divide trial 2 by trial 1, and we're just going to see what we get. So for trial 2, I'm going to go ahead and look at my rate law first, or sorry, my rate. So 3.3 times 10 to the negative 2. I'm going to leave my units out here just for the sake of space. Equals K times, and so K is that our constant, our rate constant here. So rate equals K times, and then whatever A is to the X, B is to the Y, C is to the Z. So K times 0.25 to the X times 0.10 to the Y times 0.10 to the Z. So we don't know what those exponents are. That's what we're trying to find here. So that was trial 2. I'm going to divide all that by trial 1. So I'm going to take the numbers from trial 1. I'm just going to divide. So 5.2 times 10 to the negative 3 equals K times, and these are all 0.1, 0.1 to the X, 0.1 to the Y, times 0.1 to the Z. Alright here, so when you're dividing, anything that's the same on the top and bottom are going to cancel out. So now we don't have to deal with this, this, or that. And when we plug this into our calculator, we'll see that we get 6.35. When you divide these numbers by one another, 6.35 equals 2.5 to the X. I hope you remember your log rules here because we're going to need to use logs. So log base 10, not natural log, so make sure you're not using ln on your calculator, you're using log. So based on the law, or the definition of a log, the log of 6.35 equals x times the log of 2.5. And I'm just going to rearrange this. So using, again, another definition, that means that the log of 6.25 divided by log of 2.5, that's going to give me whatever x is. And in this case, when I plug all that in, I find that that equals 2. So that means this x, or this exponent, we know is 2. Okay, let's find the y. So I'm going to switch colors to keep these separate. So for y, I'm going to call my y my h plus. And for h plus, I'm going to compare two trials again. So I would like you to find the two trials you compare, and then work all of this out. Get all the way to the final number. Go ahead. Okay, so hopefully you picked trials 1 and 4. And so I'm going to compare trials 1 and 4. So I'm going to take trial 4 and divide it by trial 1. So 7.4 times 10 to the negative 3 equals k times 0.10. Now I know my x is 2. 0.10, I still don't know y. And 0.20, sorry, z. And those are our numbers from trial 4. Divided by trial 1 here. So my numbers from trial 1, 5.2 times 10 to the negative 3 equals k times 1.0 squared, because we know that's a 2. 1.0y, 1.0 to the z. And we're going to cancel out things that are the same on both sides. So k's, those are the same, and those are the same. So we're going to get our z here. So plugging this in, you get 1.42. Just divide these numbers by one another, equals 2 to the z. So let's figure out what 2 is by using our log rules. So again, log of 1.42 equals z. So just bring that exponent down there in front of the log, times log 2. Rearranging that over here, our z equals log 1.42 over log 2. And plugging that in gives you 1/2. So that exponent is 1/2. So your exponents definitely can be fractions there. Don't shy away from the fractions. Okay? Let's do our ClO3 minus. So again, go ahead and pause the video and see if you can figure out what this is. Okay, so you should have chosen to compare two trials. In this case, I chose trials 1 and 3. So there aren't two trials that just have the ClO3 changing and nothing else. So we want ClO3 changing, and we're going to have to deal with something else changing too. So I chose trials 1 and 3. So I'm going to take trial 3 on top, so 6.4 times 10 to the negative 2 equals k times 0.20 squared, 0.30 to the y times 0.10 to the 1/2. Divide this by trial 1, and that rate is 5.2 times 10 to the negative 3 equals k times 0.10 squared, 0.10 to the y, and 0.10 to the 1/2. Canceling out my like terms, k's cancel out. These guys cancel out over here, so I have two terms left. So how do I do this? Well, you just do it in the same way. So plug this into your calculator. 12.3 is, that's what that's divided by, equals. And then this is going to be 2 squared times 3 to the y. So taking 2 squared, and you're going to subtract whatever that is from 12.3, so that ends up being 3.08 equals 3 to the y. Now this is pretty close. So you don't need to use any log rules to figure this out. It's going to be 1. It's going to be close to 1. So 3 equals 3 to the first power. So we can say that y equals 1. That's going to be close enough for us. Okay, so then overall we can say what our rate is. I'd like you to try to write the rate law. Now the rate law, keep in mind, should look something like this. Instead of using A, B, and C, use the actual chemicals. Use MnO4-, use ClO3-, use H+ in those brackets. So go ahead and pause the video now and try to write that rate law. Okay, so hopefully you got rate equals K times the concentration of MnO4 minus, that was second order with respect to MnO4 minus, times our H+ concentration, and that was 1/2 order with respect to H+, times ClO3-, and that was first order. Or sorry, yeah, that was first order with respect to ClO3-. Now the order that you write these in doesn't matter. What's important here is you have rate, don't forget the K, you have your brackets showing your concentration, and you have your rate law here. So you have your orders with respect to each individual reactant. Now remember, the products don't matter when it comes to rates. The only thing we care about here is the reactants. Now we're going to calculate the rate constant, or the value of what K is. So we're actually going to get a number and some units for K. And to do that, the only thing I need to do is set everything equal to K. So what I'm going to do is divide both sides by all this stuff here, and then I'll get rate over that equals K. So just algebraically rearranging that equation. So rate over concentration of MnO4- squared times the concentration of ClO3 minus the first power times the concentration of hydrogen ions to the 1/2 power. And now and that's going to equal K. Now the only thing you need to do is take the data from one of these trials. You can choose any trial you want. I'm just going to choose trial 1 because it's nice and simple. It's 0.1, 0.1, 0.1, and there's our rate. So we have our rate, we have all 3 of our concentrations, we have our exponents, and at this point you just plug it in. So you can use any trial. Okay. So plugging all that in, my rate is 5.2 for trial 1. 5.2 times 10 to the -3, and that's in molar per second. Divide that by 0.1 molar squared, so we're just going to carry that squared. 0.1 molar the first power, and then 0.1 molar to the 1/2 power. Plugging all that into your calculator, you should get 16.4 molar. And then how many molars are you going to have? You should have -5/2 times inverse seconds. So you have -5/2 for your molars, right? And then you have your inverse seconds, as it's going to cancel on over. So this is going to be what your value for K is, including units. And for every reaction, you're going to have different units. So make sure you work that through. Yeah, you're just going to have different units, and most of the time they're going to look funky like this, and that's okay. Okay, let's calculate now the rate of disappearance of MnO4- if these are the concentrations. These are going to be your starting concentrations, so we're not going to use that data from any of the trials above. We're just going to plug in these ones. So the rate of MnO4- disappearance is going to be equal, so the rate, we're just going to use that rate law again, equals K times, I'm just going to copy it down, MnO4- squared, ClO3- the first power. And you don't have to write the 1 if you don't want to for the first power. I'm just writing it. H plus to the 1/2. I'm just writing that for clarity to show you. So plugging everything in here, so we know what our K is because we just calculated it up here. So our K is 16.4 molar to the negative 5/2 times inverse seconds. Multiply that, and we have 0.2, 0.2, 0.2, so for all our concentrations, so those are all going to be the same. So 0.2 molar squared times 0.2 molar, the first power, times 0.2 molar to the 1/2 power. So plugging all of this into your calculator and keeping careful track of your units, you should have 5.9 times 10 to the negative 2 molar per second, or moles times inverse seconds, however you'd like to write it. I would like you to please take a second and make sure that you can actually get that number out of your calculator, and you can follow through with the units to make sure you have the correct units. Okay, lastly, for trial 2, find the rate of appearance of ClO4 minus. Alright, so the rate of appearance, so we're going to use our change in concentration over time here. We don't need to use our rate law for this. So the change in ClO4 minus over the change in time. So if we look at our equation, the rate of ClO4 minus here, and that's our product here, is 5/2 the rate of MnO4 minus disappearance. So for every 2 of these guys that get used up, 5 of these guys get made. So our rate is 5/2. So I'm going to take that 5/2 as our stoichiometric coefficient and multiply that times the change in MnO4 minus over the change in time. Okay, so where did we get this again? This 5/2, this is our stoichiometric coefficient. So what that means is that the ClO4 minus increases in concentration at 5/2 the rate that MnO4 minus decreases in concentration. And from that, and you get that from the balanced equation. So C balanced equation. Okay, so that's our stoichiometric coefficient, and this is our rate, so this times the rate. So, and that's going to equal, we're just going to carry that 5/2 over, times, well, the change in MnO4 minus over time, that's just our rate, and so that rate is actually given to us here, so we can use this rate here, we can really use any rate. Okay, and then plugging that in, you should get 8.3 times 10 to the negative 2 molar per second. So that means if the rate of MnO4, I'm sorry, you can barely see that. So if the rate of MnO4 getting used up is 3.3 times 10 to the negative 2, the rate of appearance of that product that it's making, that it's turning into, ClO4 minus, is 8.3 times 10 to the negative 2. Okay, that is the end of video 2.1.2, and that's the end of lesson 2.1 on rates and rate laws.